than what we were dealing with about an hour ago. Is this time I guarantee that the array is sorted, in this case, in a non-decreasing way. In other words, non-decreasing means that I can have another element of the same value. As long as this is not less than this one, we are fine. So now the question is, how is that going to help me in terms of doing a linear search? So we're not doing binary search or any one of those more advanced techniques. We're still doing linear search. Let's say this time we're looking for the value 6. Okay? So we still start from the beginning. We compare 6 to 2. 6 is greater than 2. We say, okay, that's not what we want. Do we know for sure now that the rest of the array cannot contain the value 6? No. Okay, then we look at the next one. We say, how does 6 compare to 5? 6 is greater than 5. Do we know at this point we can rule out the rest of the array? No. Now we know we compare to 10. 10 is greater than 6. Can we now rule out the rest of the array?
Yep.
Yes, we can, because the array is already sorted. Even though I don't know at this point this is 11, I know this is at least 10. Now, as long as this is at least 10 and 10 is greater than 6, I know this one is greater than 6, and the same applies to everything on the right-hand side.
So you don't have to go further.
So we can exit earlier from the loop. Okay? So that helps in terms of looking for a particular item. But what if I'm looking for 21? Would it help? No. If I'm looking for 21, by the time I compare to 14, I still don't know that I still cannot rule out the rest of the array, because 14 itself is still less than 21, and I cannot use that trick anymore. Are we okay so far with this approach? It helps a little bit, but it doesn't really help a lot on the average. Okay? If you think about what you're searching for, let's just say that the value we are searching for is somewhat evenly distributed within the range of the values of the array, then it can only help you half of the time on the average. So on the average, using this trick with a sorted array, you can reduce the number of iterations by about a half. If you have 1,000 items, the average number of iterations will be around 500 or so. And that's assuming your distribution is even across the entire range. Is that making any sense? Okay. That basically covers the first part, up to section 3, linear search, and how do we optimize our linear search algorithm when you already know an array is sorted. And that's not very helpful. Okay, linear search is actually a very poor search algorithm when you already know an array is sorted. The best way to do it is to use a binary search. Okay, so we're going to kind of skip some of that stuff. You can read it. You have to read it by yourselves. But there's really nothing really, fundamentally different compared to the previous chapter. But this is different. Binary search is very, very powerful, because what it does is, if you have a stack of cards, each one has a number on it, and I ask you to look for a specific number, and you already know the deck of cards is already sorted, binary search means I'm not looking from the top, I'm not looking from the bottom. I take the middle card out of the entire deck. I look at that number, and only 3 things can happen. 1, that card is exactly what I want. Well, that's good. I can stop the search right away and say, I'm lucky, I got a number that I'm looking for. And then the second thing that can happen is the card that I pull out of the deck is less than what I want. If the card is less than what I want, I also know that the top part of the deck cannot have the value that I want, because every single one of those cards has to be less than or equal to the value that I'm holding right now on my hand. So I can basically toss away 1/2 of the deck with one single comparison. The remaining portion, I can do exactly the same thing. I pick the middle one out of the remaining portion of the deck, and I say, okay, which half do I throw away? Throw away the top half or the second half, and then I can reapply the same technique. It does not sound like it is a very powerful technique, but it does. But it is a very powerful technique. To show you how powerful the technique is, how many times do I have to compare? If I have this many entries in my array, this is about the population size of the world at this point, 8 billion people or so. If I have one single directory, a single array for every single person on this world, okay, sort by some means, okay, but it is sorted. How many comparisons do I need to confirm what I'm looking for is not in the array?
32, 33.
Exactly, it is 33. Okay, we know it's 33 because if you look at this number and you say, okay, what is the closest power of 2, to this number? 8 is 2 to the power of 3. That's easy. Every 1,000 is approximately 2 to the power of 10. So that's only an approximation because 2 to the power of 10 is 1024. But sometimes for the order of magnitudes, we call 1024 close enough to 1,000 just to estimate what is the range of numbers we're dealing with here. So we have 2 to the power of 10 here, 2 to the power of 10 here. We multiply all these things together. So this whole thing is about 2 to the power of 33. And because it is 2 to the power of 33, we know that in order to confirm that one thing does not exist in this array, we only need 33 comparisons. What if the world population doubles again? Well, first of all, we'll all die from hunger, but assuming that we don't die from hunger, how many times do we have to search in this array to confirm that one particular item does not exist?
66.
No?
34.
34. Okay? You double the size of the array, you add one comparison. Now that is powerful. Okay? Are we convinced that binary search is inherently efficient? In fact, when you go to a 4-year university and you take the class called the Analysis of Algorithms or Algorithm Analysis, they will show you that you cannot search any more efficiently than binary search. Okay? This is proven to be the most efficient way of searching. There's no way that can be faster than a binary search algorithm.
Can you explain why you use 2 again? Just because it's...
Because every time you have it, if you start with 8 billion, after one comparison, you only have 4 billions left.
Oh, okay.
With 4 billion, you have one more comparison, you have 2 billions left. So every time you're reducing the size of the array, or you're reducing the range of the array that can contain the value by half. So the question is, how many can you have 8 billion before you have a single record left? Because when you have a single record left and that is not what you want, then it does not exist in the array. Okay? Do we have any questions about the basic idea of binary search? No questions? Okay. If there are no questions about the general approach, we'll go ahead and try to write the algorithm for binary search. But before we do that, it is helpful to have a few examples. So this way we can try to come up with a systematic way of doing this. I specifically start with an array with 7 elements because everything divides really nicely when you have a power of 2 minus 1 as the size of the array. 7 is 2 to the power of 3 minus 1, so it works out pretty good. And I'll give these specific values. You can have duplicate values. That's not a problem. Okay, you can skip values for with a large range. That's definitely not a problem. Okay, so let's just say that this is the array, and those are the values in the array. We have 2, 2, 4, 10, 100, 101, and 120. What do you guys want to search in this array? As an example, doesn't really matter.
17.
17? Okay, let's search for 17. So k equals 17. K represents the key, and we want to locate an item in the array with a value of 17. Now, with binary search, we search from the middle. In other words, in this case, which element is the middle element? A bracket 3 is the middle element. So we first compare 17 to 10. The relationship between 17 and 10 is 17 is greater than 10. Okay? What do we do? Which can we throw away one half of the array? We can throw away which half? The left-hand side, right? Because the relationship is this. So now we can eliminate this entire side. So this side is entirely eliminated. It does not mean that I have to delete these entries from the array. I only need a way to mark the array and say that nothing up to a bracket 3 can contain the value that I'm looking for. Which means the only remaining portion of the array that can have the value that I'm looking for would be a bracket 4, 5, and 6. Right? I reapply the same approach. What is the middle element within the range of the array that can still contain the value that I'm looking for? 5. Very good. So we compare 17 to 101, and the relationship is like that. So now what do I throw away? I can use 5 and 6. A bracket 5 and a bracket 6 are now eliminated. So that part is now eliminated. I have one choice left. I have a bracket 4 that has not been ruled out. So in this case, I have a third comparison, comparing 17 to 100. And obviously, the relationship is 100 is greater than 17. So at this point, I can also say that this part is now eliminated. Do I have anything left?
Nope.
Nope. Since I have nothing left, I now can conclude that 17 is not in the array at all. Yep.
When you divide your remaining array by half, and if you run into a situation where you have an even number of elements, are you supposed to add 1 or subtract 1 from the number of elements?
If you have an even number of elements, which means this would have been 7 or something like that,
right,
then the middle index would be like something and a half, like 3.5.
Right.
Then you can either use round up or round down. Either way is fine. Doesn't matter.
There's no advantage to either.
No, there's no advantage to either. Taking the floor or the lower one, or just the integer portion of the fractional number, is automatic in many cases, and that's how people usually do it. It doesn't cost any extra computation to get to the integer part of a mixed number. Okay. So it looks like we have a fairly good handle of how to make this work. So the next thing we want to do is to try to write an algorithm to do exactly that. We'll go back to our text editor and write this algorithm. This time we are writing the binary search algorithm. Now, I could have just read the algorithm from my notes and trace it and call it a day, but I want to explain the process of writing an algorithm. How do you get started? How do you go from one step to the next, and so on and so forth? I can only do that kind of in emulation. In other words, what I'm doing right now is not the true process, the thought process that I went through when I wrote the algorithm. That is so long ago, I could not remember exactly how it was done. So this is more or less a backtracking or an emulation of the thought process to create or to write an algorithm. But I think it is still better than not showing it at all, because I think there's still logical steps that you can take when you are constructing or writing an algorithm. Revision 1. This is a search algorithm. Is this process repetitive?
Yes.
Okay, it is repetitive, so we know we have a loop of some kind. When do we get out? This is a search algorithm. Well, when we get out of a search algorithm, it is all the same. In other words, I can copy and paste from the linear search algorithm and say that, overall speaking, at the highest level, this is exactly what a binary search